Hi, welcome to our last example in 2.5 stretches of functions. In this example, we're looking at something called simple harmonic motion. Simple harmonic motion refers to objects that travel in cyclical patterns or in basically cycles that can repeat. So examples of this can be like a pendulum that swings back and forth. Another example, like what we're going to look at here, would be a spring with a mass attached to the end. And you pull the spring down, and then it kind of oscillates up and down, back and forth, and the motion keeps repeating. So in this example, we have a mass on a spring, and it bobs up and down. Okay? The period is the amount of time that it takes for the mass to move from its starting position to the top, then to the bottom, then back to the starting position. Okay, so one full cycle. The period t is in seconds, and it's given by this equation here. So in this equation, we can see that t, which is the period, it's a function of m, where m is the mass. So we can see the mass is in the equation right there. The mass is measured in kilograms. And then we have another uh, variable in there, and it's the spring constant. So usually this is a measured value that's given for any type of spring. So all springs have different spring constants, and they're measured in newtons per meter. So basically what the spring constant is it tells you how soft or how stiff the spring is. So if you have a high spring constant, it just means it takes a lot of force to stretch it a meter. So it's like a really hard, tight spring. If you have a soft spring, it just takes a little bit of force and you can easily stretch it. So the ideal spring company needs to show how each of their spring performs compared to others. So they have the basic spring, which has a spring constant of 100. The strong one is double that, 200 newtons per meter. The heavy duty, 300 newtons per meter. So we're asked to graph the period versus mass for the various spring constants. So we want to do T versus M. So we can easily take these values for K and plug them into the equation. So we'll do the first one in black here. We'll say T of M. I'm going to insert, these are my values for K. So I'm going to put 100 in for K. So we'll have 2 pi times the square root of M, that's my variable, over 100. Okay, so now we can see that T depends on M. So I can also see in this equation that as mass gets bigger, this equation is going to get bigger too. That the period's actually going to get longer. So as M goes up, T is going to go up too. Okay, the next one, I'm just going to color code these. So the strong spring, T of M is going to be equal to 2 pi times the square root of M over 200. And the last one in green, heavy duty spring, we'll say the period is equal to 2 pi times the square root of M over 300. Okay, make sure you draw these roots over top of, like include the whole fraction, right? Okay, let's get ready to do our graphs. So we'll do the t-axis here, time. Okay, it's going to make that a bit darker. And then our independent axis is m. Okay, I've already kind of graphed this, so I've seen some values for it already. I kind of know how to set this up. So we have 0.4, we can do 0.8 here, and then we could do 1.2 there. So that's the mass in kilograms. So we're starting at like 0, then we have 0.4 kilogram, 0.8, and then 1.2. Now the period, this is the times that it takes to do one full cycle. Those are actually very quick. So we will do let's do 0.2 here, 0.4, and then 0.6. Okay, so those are going up by 0.2. So the first one, the basic spring, we have a starting point at 0, 0, and then at 0.4, we're actually at 0.4 again. So we have this next point. At 0.8, we're just below 0.6. So we're about right here. And then at 1.2, I know we're just below 0.7. So that would be just below right there. Okay. You might think this is linear, but it's not. Um, it's actually starting at the origin, and then it looks like our square root graph. So that is T of M for the, actually let's just write this, the basic spring. We'll just write that here, basic. All right, now our strong spring with a spring constant of 200, this one's in red. So we still have a point at the origin. So when M is 0 in here, this whole thing is 0. And then if we were to plug in 0.4 in here, we end up getting a value for T at just below 0.3. So right there. And then if we plug in 0.8, we actually get about 0.4. And if we put in 1.2, we get just below 0.5. So again, we got a nice curve going through here. Okay, and those aren't exact, they're just kind of close approximations. Okay, and now our heavy duty spring. So we still have 0, 0, and at 0.4, we're at just a little bit above 0.2. And then at 0.8, we're just above 0.3. And then at 1.2, we're just below 0.4. So this goes through those points like that. That's our heavy duty spring. Okay, so those are the three graphs for the various spring constants. How are the graphs of the strong and heavy duty springs related to the graphs of the basic spring? Okay, so if I compare, you know, if I kind of compare these, I can actually say like the strong spring is actually just 2 times the original spring. So if I call this one K, let's see this in black here to keep it color coded, then the strong one is just going to be twice the amount, so I could call it 2K. And the heavy duty one, sorry, let's go back here, the heavy duty one, I could call it 3K. So the reason why I call it 3K is because if this is a spring constant of 300, it's 3 times the size of the basic one. Just like this one is 2 times the size of the basic one. So if I look at it this way, and remember K is in the bottom of the equation, I can actually think of this as being doubled for the strong spring, or I can think of this as being tripled for the heavy duty spring. So how does that affect the graph? Okay, if I do that. So what I can actually think about is I can say, okay, well, if I'm going from here to here, I've actually what I've done is I've caused a horizontal stretch by a factor of 2. Okay? So if you think about it, if I were to take this and if I were to multiply this by a half on the inside, so if I could multiply that by a half, I would end up getting this. So that would represent a horizontal stretch by a factor of 2. For this one, to go from here to here, it's like I'm multiplying by 1 over 3. So that'll be a horizontal stretch by factor of 3. Okay. So remember, if you can tell that you're multiplying by something small, you know it's going to be bigger and it's going to become a stretch. Okay, that is it for the last example, and I'll see you guys in the next lesson.